check. But I also spend time at Case Western, where I thought I saw some name tags from Case Western here, and I've been spending more time at Ohio State. And I think I know I've seen some Ohio State graduate students, so I just think we should applaud the bravery of all of us of coming this 3 hours north to participate. I realize that I'm the early universe person here. That was what was on the that was the stand-in for my title for a long time. So I decided I'm going to start pretty basic. And I think if I'm going to talk about the early universe, it's really important for me to talk about inflation. But I hope to do it maybe through a slightly different lens than you're used to, or at least through a lens where we can see how the dynamical system inflation really works. So I'm going to start by just reminding us, although maybe some of us really don't want this reminder and others maybe need this reminder, but I want to remind us about how the universe is a dynamical system, if only to give us a common language to use when we're talking about the early universe. Then I'm going to talk just quickly about what's wrong with the standard Big Bang model and why inflation is something that we need, why inflation cures these problems, and then actually I hope to spend quite a bit of the time in our first 40 minutes doing a quick little numerical simulation of inflation, just so that we can actually see the dynamical system come to life, and we can see how the tools that we use produce an inflationary model. And then we'll have more fun as the couple of days go on. For today's 2 lectures, I've really been looking back at a number of the references that I've loved to read over the years that talk about the general picture of inflation and inflationary perturbation theory. I list some of them here. This is not exhaustive, but these are the things that I had on my desk for the last week or so while I was planning this lecture. And so I want to make sure I give credit to the others who have made great exhaustive reviews of the topics that I'm about to talk about. Finally, before I get into it, we have to agree on convention. So I'm going to use so-called natural units. We used to call these God-given units, but natural units where h bar and c are equal to 1. But because we're not purely relativists, we're going to retain the dimensionality of Newton's constant. And so the g is not equal to 0. The g is something that has dimensions for us. And sometimes I will parameterize that in terms of the reduced Planck mass, which is the capital M. Other times you will see the regular Planck mass, which is the lowercase m, appear in some of the figures, especially if I take them from other places. But that is really to remind us that gravity has a scale, and that scale is g. Okay, and so we will keep units as much as possible. And I'm going to be using the mostly plus metric convention, which I recently learned was the East Coast convention. I don't know if that's a well-known thing, but anyway. Okay. So you've probably heard of the universe. Yay. Trying to get a little interaction here, right? Woo, right. Yay, okay. So in order to take the universe and turn it into an actual dynamical system that we can write down, we have to make some assumptions about it. And so we start with the cosmological principle. Again, I think maybe we've all heard these words. I think if you didn't, Maya's talk this morning might have been a little difficult to follow, right? But the idea is that we impose the cosmological principle, which states the universe is homogeneous and isotropic at large scales. This is supported, it has historically been supported by views of the contemporary universe that are statistically the same, right? So I have on the left here a picture of the Hubble Deep Field. Just looking at it, there's no way you can tell what direction the camera's pointed, right? So the universe is homogeneous and isotropic. More contemporarily, we've actually been arguing that the CMB might be a better indication of the cosmological principle of homogeneity and isotropy. Maybe I'll muse on that if anybody wants to buy me a drink later. But I will pause. So we will assume the cosmological principle for the remainder of today and probably throughout all of tomorrow. I do want to say it is one of my great pastimes to wonder why we talk about the cosmological principle. And maybe you can help me out with this, right? So you're all physicists. If somebody says, blah, 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 on large scales, your response has always been, Good, how large compared to what, right? Right. Yeah? Right. We've always, whenever we've done perturbation theory before, we've always talked about comparing it to some physical scale. And when you ask cosmologists, what is that scale that we're comparing large to? The answer is often not actually received. So something I think about a lot, but I won't talk about it today. So if I have the cosmological principle, what I end up with on the left-hand side of Einstein's equations is I have a metric. That metric has components now that only depend on time, right? They can't depend on space because that's the symmetry that we imposed before we wrote down this solution. There's still one open thing in the FLRW metric, which is this factor k, which can parameterize the global geometry of my space surfaces, my spatial hypersurfaces. We'll come back to that in a second, but basically k is a parameter that's not set by isotropy and homogeneity. The other thing that appears in the metric is, of course, this a squared, right? Which is the expansion, which is the scale factor, which compares the physical sizes between co-moving observers from one time to another. And of course, all of these things only depend on time because we've imposed the cosmological principle, and therefore the scale factor can be at most a function of time. And on the right-hand side, we have a stress energy tensor, right? In order to solve Einstein's equations, I have to say what is the universe made out of. And so generally, we're able to write down that stress energy tensor as a component that talks about the energy density, which is rho, and components that talk about the the isotropic pressure, which we're going to call P. These two pieces are all we need to describe what is our favorite thing in the universe, which is a set of ordinary differential equations, right? Where I can talk about how is this, that was a nice joke, guys. Right? You're like, but it really is my favorite. Anyway, so on the left-hand side, I have the differential equation that comes from looking at the 0,0 component of Einstein's equations. Historically, we've called this the first Friedmann equation, and I would like you to never say that. I'd like you to call this the Friedmann constraint, because in and of itself, the Friedmann constraint, while a valid differential equation, is not actually sufficient to evolve anything. Right? It actually tells me the relationship between H, which is A dot over A, and the energy in the universe. The proper Friedmann equation comes from the II components of Friedmann's equations, which actually give me what I expected all along, which is a second order differential equation. And now I have rho and P that both appear in here, and I can fully solve this equation for A of T. Okay, and so I think as we're learning more about how to study this system, it's really clear that the second Friedmann equation, or the actual Friedmann equation, is the one that we really should look to when we're looking for the dynamics of the scale factor. I can combine these two, right? You'll notice I still have this k floating around, which makes this a little bit uncomfortable. I promise I'll get back to it. Okay? But I can combine these two to come up with a differential equation now for rho, which tells me how the density, or how the energy density of the universe is changing, based again on what is actually part of the universe. Okay. And this really, because it's rho dot, right, and rho is H, this is really a statement of the second order differential equation. This is a statement of how is A double dot changing when talking about this stuff in the universe. But we like to write down the continuity equation because all I need is chemistry to turn the continuity equation into something that I can directly integrate and solve. Right? I think maybe we've seen this before, but if I talk about a homogeneous and isotropic universe where the pressure depends on the density, right? So it has an equation of state. Then I can fully determine how rho evolves, right? How is the energy density changing? Purely by knowing what that equation of state is. And so how do we know the equation of state? Well, as I said, we get that from chemistry or by actually just looking at the system, right? So if I have a box of rocks out in the universe, they're pressureless, but they have an energy density. As the universe gets bigger, rho decreases by a to the minus 3, and that's consistent with an equation of state that's equal to 0, right? So that's your pressureless fluid. If I have a box of photons, as the universe gets bigger, the density of photons drops as the volume, right? So it's a to the minus 3, but each photon also gets stretched out. And so we get an extra factor of a when I convert that to energy, and the energy density drops off as a to the minus 4, and that gives me an equation of state of a third. And if I happen to, for no particular reason, see a component of the universe that doesn't dilute as the universe gets bigger, I can actually find out that that corresponds to an equation of state of minus 1. Okay? And so Friedmann equations now, they give us an ability to both find out, well, what is the density of the universe doing as a function of time based on what it's made out of, and and then from that we can get what the scale factor looks like as a function of time. Okay. So to go back to Friedmann's equations just for a second, because I've been skipping over K, and I skip over it basically because I don't really love it. But that, again, another story that has to do with scales. But if I go back to the Friedmann constraint, I can clearly see, right, that there is some critical density if I look at this equation. And if the universe happens to have this critical density that is equal to 3h squared over 8 pi g, and this is a time-dependent statement, right, because h, the Hubble parameter, depends on rho, right? But if I measure the density of the universe to be exactly equal to 3h squared over 8 pi g, then this parameter k is equal to 0. And the parameter k equal to 0 in our minds means that my spatial hypersurfaces are flat, right? That triangles add up to be 180 degrees, and there's all this consequence that comes along with k equal to 0. But I actually like to think about this not just as the flatness of the universe, but I like to think about it as the fact that the universe maintains the critical density. That is to say, this existence of the critical density actually allows me to say how close is the density of the universe to the critical density, and will it stay there? Right? So I calculate the combination omega minus 1 over omega, which is the fractional change away from the critical density, from the critical density. This thing is a time-dependent quantity, and it depends on 1 over a squared rho. Right? And I'm saving you from some of the algebra of that, but you're all capable of it. So if a squared rho grows with time, then the universe will stay it's a detractor, and the universe will stay at its critical density as a function of time. But if a squared rho gets smaller, then the universe staying at its critical density is an unstable point. Okay? And the universe will diverge from being at its critical density. And of course, you say, well, that's all fun, right? But of course, on the previous slide, right, we were able to write down what rho looks like as a function of a. And so for anything that we're used to, if I'm talking about matter, I'm talking about radiation, rho either goes as a to the minus 3 or goes as a to the minus 4. Well, a squared times either of those goes as either a to the minus 1 or a to the minus 2. Which means that for a universe that's filled with normal stuff, the critical density of the universe is an unstable point of equilibrium. That the universe will diverge from satisfying the relation will diverge from the critical density. And of course, measurements of this parameter these days actually tells us that, well, maybe omega minus 1 over omega is 10 to the minus 5, maybe it's 0.3, maybe it's 1. Anyway, it's some order 1, it's some small number, which means that in the past it had to be super, 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 super small. Okay, and that's what we call the flatness problem, is that normal stuff makes the universe diverge from the critical density. And so in order for the universe to be so close to the critical density today, in the past it had to be extremely close to the critical density. Better to 1 part in 10 to the 17, right? If I actually showed you the derivation. Okay. More than that, you can, but who cares? You can actually solve the flatness problem just by setting k equals 0, right? Which is something we did for 60 years, from 1920 until 1980, right? Like, why not? Right? Easy way to get rid of a problem. Even if you do, what you end up with is a set of differential equations that you can solve for a. And you can find out exactly what the expansion of the history, what the expansion the scale factor of the universe look like as a function of its entire history. And it's just a differential equation, right? I can just take rho and I can break it up into the part that's matter, the part that's radiation, the part that's dark energy, and I can numerically solve that system to find out what A looked like, right? Now this is very deep, but this is 1920s physics, right? That I take this system and I look at what happened in the distant past, and I find out that from that dynamical system, I get a point where A was equal to 0 some finite time ago, right? And I don't have time in 40 minutes to tell the beautiful story of who did what, blah, 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 blah. Anyway, this led us to the idea of the Big Bang, right? That there's a finite time in the past where the universe had to have an A equals 0 instant. I was going to parameterize this just in terms of H naught because I know that there's a little bit of tension over that. Can we tell it again? No. Real tension. Anyway, but so it's actually like minus 0.9. Anyway, it's about 1 H naught inverse. But Maya convinced me that we'll go with LIGO's value of 70 kilometers per megaparsec, per second per megaparsec. And in choosing their value, that means the universe is 13.46 billion years old. Okay? All of this comes from that simple dynamical system. However, oh yeah, I already said this, so I don't need to say it again. Okay. Okay. So that is our Big Bang cosmology. I've already said that there are some problems. There are some issues that come out of this because we had to gloss over the flatness problem, right? That the universe diverges from its critical density. There's also something called the monopole problem, which is that if you had gut scale physics, that gut scale physics should have produced magnetic monopoles. The abundance of that magnetic monopoles would have meant that we would have encountered them in astrophysical probes today. We haven't, which you remember from your E&M class, right? And therefore, where did all the magnetic monopoles go? Right now, again, this assumes something about that you have some model of gut scale physics and that it produces magnetic monopoles, but in general, those statements are true. Again, I can gloss over that by saying there just is no gut scale physics. That shouldn't be recorded, by the way, okay? But even if you get rid of the monopole problem by getting rid of string theory, and then you get rid of the flatness problem by setting k equal to 0, you still have a problem that the CMB is really uniform. Okay, and this is why the horizon problem ends up being my favorite problem, because I haven't found anybody to get around it. Right? There doesn't seem to be a way to get around the fact that even if you add band-aids to your cosmological history, we still have a problem that the CMB exists and it was created at a particular time, right? So the CMB has redshift of about 1100. So if I take this numerical model that I have and I go back to when A was 1 over 1100, I can actually identify in the model the instant where the CMB was emitted, right? So on the left-hand side, it's really hard to see. But on the right-hand side, I've blown up that initial place so that you can see there really is a moment where this red line, which corresponds to the redshift of the CMB, intersects my cosmological history. And it tells me that the CMB was created about 300,000 years after this singularity. Right? This is also something you've probably been told. But because I have the expansion history and I have the existence of the CMB, I can actually calculate two really fun things, right? As fun as that. But anyway, from looking at photons, I can find out, starting from that singularity, how far could information have gone? Right? How big is the forward light cone from the singularity to the creation of the CMB? And I can compare that to how much of the CMB can I see by looking backwards in time. Okay? And I have A of t, right? And all I need to do to calculate the space-time interval is know what A of t is. So combining those two things together, I get that the forward light cone in these co-moving units is like 0.06, and the backwards light cone is 2.25. Which means that in the CMB, there should be regions that are approximately 1%, the size of the CMB is across, where I have causally connected physics. Okay. But that's not what I see with the CMB. I see a CMB that's all causally connected, right? The CMB is homogeneous to 1 part in 10,000. That's more pure than than diamonds that you buy for lots of money, right? It's much purer than the temperature in this room. It's much purer than just about any physical system that we have, which means that the homogeneity of the CMB should be broken by the fact that these little causal patches should exist. And I should at least see them in the statistics when I study the CMB, neither of which are true. And so the horizon problem says, in a sentence, that the CMB is causally connected, which is not allowed given the model that we have. Right? It's just not allowed given the standard Big Bang model. And so the story goes, right, that Alan Guth was, and I should say Linde was also working at this at the same time, but Alan's a really nice guy, and so I'm going to talk about him. Plus, he has lunch with me, and Andre doesn't. So the story goes that Alan was thinking about the flatness problem in particular, but also the monopole problem, and was wondering how to, is there a way to take these two issues and get rid of them, or at least understand them in terms of what we now call non-standard expansion history. And I'll talk a little bit more about that tomorrow. But the idea was that if you add a period, right, an epoch, in the early universe before the CMB was created, where the equation of state did something crazy, right? The equation of state was less than minus a third, then the scale factor starts accelerating, and that changes the story of all of the observable things that we've been talking about, right? Because, let me see if I have it on the slide. Okay, so for the horizon problem, what it does is it takes that causality, and rather than worrying about the photons moving apart, it actually says, well, there's so much space generated in between those two co-moving observers that the physical size of the forward light cone is now huge, right? Because the universe accelerated in expansion. If I go back to the flatness problem, if the universe is accelerating, then rho is not diluting faster than e to the minus 2. And so the universe is pushed towards the critical density rather than diverging away from the critical density. And of course, it just gets rid of the monopoles because everything dilutes really fast, right? And so as a paradigm, inflation has been able now to solve either through beautiful ways problems that we solved through unbeautiful ways before, but it also describes the CMB in a way that's really compelling. Now, of course, what's missing from that to make it science is a prediction. I'll get to that in the second half of the lecture this morning, okay? But at this point, it's at least a way to understand the observations that we have of the universe. Now, again, just if you will, well, you have to allow me because I'm up here, but as a musing, I also want to say that the introduction of inflation actually, from a mathematical standpoint, does something far more interesting than just adding another epoch. It actually changes what we mean by the initial condition problem. Because the introduction of non-standard cosmological histories at that time, especially with an exponentially expanding scale factor, might not mean that we have an initial zero volume, A = 0 point in the finite past. Right? And so that's something that we have to deal with and we have to contend with, although, again, it's not a point for today. But inflation does not solve the initial condition problem, but it does very effectively redefine the initial condition problems in ways that I think are really exciting. Okay, how am I doing? I gotta speed up. Okay, so you've seen scalar fields. If not, they are the cosmologist's absolute favorite tool. And I'll show you why they're our absolute favorite tool in a second. But basically, a scalar field, which is a degree of freedom that exists everywhere but only has one number. I can calculate all sorts of things, characteristics about it. The first thing I show is that you can calculate the stress energy tensor for the scalar field by looking at, just by looking at the action. And we find out that both terms, the stress energy tensor, the energy density depends on the kinetic energy of the field. It also depends on how bendy the field is. Right, that actually is, we call it usually gradient energy in the numerical community, although it's really just kinetic energy, right, in a different reference frame. And then it depends on perhaps an associated potential with the field. The pressure, on the other hand, depends on the same three quantities, but with different ratios. And the reason that's so cool, at least to me, and the few people that are still my friends, the reason that this is so cool is because I can now take this one object and I can actually get different kinds of equations of state from it. Right? So for example, if I talk about a homogeneous mode that's oscillating about a quadratic minimum, right, which things tend to do when you talk about minimums, they tend to be quadratic, well, then the average equation of state, although it does oscillate between 1 and -1, ends up being 0. Right? So a scalar field can mimic a matter-dominated universe. If instead of having that scenario, I have just waves in a massless scalar field, so I set the potential to be 0, and I talk about just having modes that are excited, well, those modes now have a kinetic energy and a gradient energy that are about the same, and so now it's just a matter of adding those weird coefficients, and I can get W equals 1/3. Right? So the same scalar field that gave us a matter-dominated phase can now give us a radiation-dominated phase. And if that scalar field has a potential that's really big, well, then it can dominate both terms. And because V enters with a positive sign in the denominator and a negative sign in the numerator, I can get an equation of state of -1. And so I can get an inflating universe. And so I want to be able to, or I want to be able to use the functionality of a scalar field to see if I can realize this epoch that we want in order to understand the problems of early universe physics. And so additionally from the action, I can get the Klein-Gordon equation, which again is just our second order differential equation for the scalar field. So the story goes a little something like this. For some reason, again, remember I said inflation does not solve the initial condition problem. It merely redefines it. So for some reason, I start off with a scalar field that's far enough away from the minimum so that the potential energy is really big. That potential energy really big means that the universe is going to be accelerating in its expansion, and all of the bumps in my scalar field get stretched out to the point where they're negligible. So inflation immediately homogenizes itself. But even though it's high up on the potential, there still is this dynamical system that tells me that the inflaton is going to evolve. Right, that the scalar, I should have said the scalar field is called the inflaton that's going to create. Anyway, the scalar field is going to evolve because the potential is still going to push it, right? The Klein-Gordon equation still tells me that there's a force that's going to push it towards the minimum. Sure, right? There's friction, which is going to make it move down that potential very slowly, right? But there's an elongate perhaps the time where it's potential dominated, but it's going to stay up on the potential. It's going to evolve down the potential. As it evolves down the potential, the ratio of the kinetic energy to the potential energy of the field changes. As the ratio of the potential to the kinetic energy changes, that changes the equation of state. That changes the expansion history of the universe. It lowers the Hubble parameter. It lowers the friction. That makes the field speed up. Right? This is a beautiful dynamical system that not only gives us that inflationary phase, but it also tells us that that inflationary phase can end. We're about to transition to actually doing this. And so I want to be clear that when you do numerical simulations, or you even when you're just looking at inflation, you want to be really careful about what you're defining as your time. Okay, what we've been talking about so far is so-called cosmic time, which is when the metric only has a dt squared as its first term. Other times that are commonly used are conformal time and what's called e-folding time, which measures time in the in the amount of time it takes for the universe to grow by a factor of e. For the simulation that we're going to be doing, I'm going to write it. We're going to look at it in both in cosmic time and in e-folding time. We're not going to worry about conformal time today. The last thing I want to say before I'm going to have you open up your laptops and open the Slack link that I sent you is that this period that we've been talking about where this type of inflation where I have a potential dominated model that slowly rolls down until inflation ends is literally called the slow roll regime. It's not the only way to get inflation, nor is it the only way to end inflation, but it's the one that's most commonly used because it allows inflation to end in sort of a peaceful way and allows us to get out of inflation in a sort of normal way. And because of that, we also introduce what are called the slow roll parameters, which are two numbers that kind of parameterize how slowly is the field rolling. Okay. The ones that I'm going to be using without subscript today are the Hubble slow roll parameters. There is also a potential slow roll parameter, but maybe I'll talk about that towards the end of the second talk. Okay. Just to show you a quick movie. So what's going to happen, right, or what happens, is that the scalar field starts in a potentially dominated place. The full dynamical system causes it to move slowly until such a point happens when it transitions away from an accelerating equation of state to a different equation of state. And this is the thing that we want to try to reproduce today. Normally I'd ask if there's any questions, but let's just do it. So in your Slack, is that the right phrase? In your Slack? On your Slack? If you go to your Slack, there's I posted a link that uses Google Colabs. And so when you click on it, this file should pop up. All you need is a Google account, I'm told. Okay. In the day one lectures. Okay. Let me repeat what you're saying in case people don't see it. So if you don't see it, go to Add Channels, and I think you can type day one lectures, and it'll pop up there. Once you have it, it'll appear under your channels, and then down here at the bottom is the link to the Colab. Once you do that, this little script should open up. And I've written most of it for us. I know we don't have a lot of time today. I hope, but it's something that's reusable. So think about it as like, if tonight, you're back in your hotel and you want to run some different potentials, feel free. Okay. I'm trying to give everybody a chance to open it. Okay. The other thing that seems to be important is you've opened a copy of it. So save it to your drive. And that will allow you to not lose it, okay, as we work with it today. If you don't save it to your drive, I think it will run, but then it never leaves the cloud. That's absolutely not the right way to put it, but because I think anyway, doesn't matter. Okay, so let's do it. So what our goal is the next 4 minutes is to take that system of dynamical equations, that coupled set of second order differential equations, and find out how we can use a potential to go from an inflationary period to a non-inflationary period. So the first cells that you evaluate are just to load the packages. The second set of cells that I have here are actually defined. I've put in 3 different inflationary models for us. The first one is what's called new inflation or chaotic inflation, and is ruled out by the CMB, but is a great inflationary model to look at because it is just a quadratic potential. Right? And so many of the minima that we see when inflation ends are characterized by the same dynamics as having a quadratic potential. Then there's a massless version, and then a tanh version, which is motivated by some newer models of inflation. But I'm going to stick to my favorite, which is the first one here. You may do whatever you want because you have free will, and all 3 are there. Okay? But I can't go out and help everybody till later. Okay. So you just want to uncomment the 3 different function definitions. The next set of cells will allow us to see what the potential looks like, right? And now this is not like a big surprising thing, right? Like it was a quadratic potential and it looks like a quadratic, right? But if you were to put in something more exotic, it's always a good idea to see what the shape looks like so that you can say, well, over here is where I'm going to start inflation, or over here I'm going to start inflation, and this is where I expect inflation to end. The next block of codes are going to calculate a number of the things that I've shown you on the previous slides, right? Remember I mentioned that we're going to do it in cosmic time and in e-folding time. So we've defined epsilon, the first slow roll parameter, in terms of both of those times. The Hubble parameter squared, again, in terms of both of those times. And then the equation of state, because that was, again, the thing that tells me if I'm inflating or not is the equation of state, right? That's the thing that tells me how the universe is going to be expanding. The next block actually has all of those dynamical equations, right? So this has calculating the Hubble parameter, it has the Klein-Gordon equation for the scalar field, and it has the Friedmann equation, which are going to evolve the scalar field and the scale factor as a function of time. Once you've done that, you now have some choices, right? So again, I want you to think about the fact that rather than doing assumptions on my model, I really want to see how the physics emerges just by looking at the coupled set of equations. And so a lot of this is going to be guesswork. Now, I happen to write this script, and so I kind of know what the guesswork is. But I'm going to let so in my cosmic time simulation, I'm going to let it go to 200. If that's wrong, I'll go back and fix it, right? But I'm going to let it go to 200. In the e-folding time, well, I don't know. Maybe I'll have it go to 100. Okay? Again, when we're doing this, we can ascribe some physical meaning to what these times are. In cosmic times, right, it's like the number of oscillations of the field. I don't know how many oscillations of the field it takes. In e-folding, it's how many e-foldings, right, between the beginning of the simulation and the end of inflation. I don't know that apropos, right? And so a lot of this is going to be going back and fixing things to make sure that I've fully resolved the system. And then we need an initial phi. Where is the field going to start? Okay, now in principle, if we had a lot more time, I'd say try a bunch of stuff out. So instead, put in 20. By the way, that in and of itself is also one of the great challenges of inflation, why that number is bigger than 1. But again, I'm running out of time. Okay. I will say, as a numericist, one thing that I always do, especially when I'm using prepackaged ordinary differential equation solving routines, is to look at the output of the routine to see if it thinks it worked. If it doesn't think it worked, it didn't work. If it thinks it works, it also probably didn't work. Okay? But at least we can tell sometimes when it doesn't work. For example, oh, it did work in both cases. That's unsettling. Okay? But now I can actually plot the solution, right? And now I can tell you why it didn't work. Right? Because, so on the left-hand side is in cosmic time. I can see the field kind of slowly rolls down and then starts oscillating. On the left-hand side, now this is in terms of e-folding. And so even though the velocity in cosmic time is constant, the velocity with respect to e-fold is not constant. And what happened over here is that the black curve didn't go all the way to 0, which means that I didn't integrate the e-folding time long enough. You don't have to go back and do this now, but I will, just to show you that now my integrator failed, right? And that is, again, come talk to me, right? But that is telling me that in e-folding time, this method of studying inflation is going to fail. And it fails actually right when inflation ends. And so this is why I did 2 clocks, to show you that the clock during inflation, which is perhaps the e-folding clock, is not the best clock for after inflation, right? Anyway. We can calculate other things. So we can calculate the Hubble parameter. We can see how it's changing and how it drops from some large number to almost 0 when inflation ends. We can also calculate the equation of state. I find this one really cool, right? Because throughout the inflationary period, it's -1, which we expect. Then as the field starts to oscillate, right, it goes between 1 and -1, but that averages out to 0. Right. finally, we can get I just want to do this final step. The final step is to calculate when inflation ends. And I want to show you that even in this model that we had here, right? So both in the cosmic time simulation and in the e-folding time simulation, I got a condition now on the end of inflation where the first slow roll parameter exactly equals 1. Okay, it also tells me what the value of the field is and what the value of the field derivative is. I promise to let you have your break in 30 seconds. We're going to use this again in 10 minutes when you come back. But I do want to point out that what we need to check, right, is we need to check still that this is actually the right answer. Right? Even though the integrator says that I've done everything right, in order to be physics, these physical conditions, that is, what is the value of the field at the end of inflation? What is the Hubble scale at the end of inflation? What is the slow roll parameter at the end of inflation? Those have to be independent of my numerical choices. So I have to check, well, what are my starting values? Right? If I start the field higher up on the potential or lower down the potential, do I get the same answer? We used to talk much more about what's called the inflationary attractor, which is one of the beautiful things about these mathematical models is that no matter what my initial conditions are, I hope to evolve to the same inflationary period that ends in exactly the same way. I know that these are probably pretty good, but it would be a thing to go back and check and make sure that your numerical system works okay. But what we have seen is that using this simple tool, right, I can take all of the words that I've used to describe all of the inflationary dynamics, and I can see that they actually beautifully emerge from this second order set of coupled differential equations. Okay. 10 minutes.
Break.
Break.
We can make it to even 5-minute break.
I'm not an ogre.
Are you ready for break?
I think so.
Let's
Yeah.
take a break.
Yeah.
They may have taken away the breakfast stuff, but let's take a little break.
Okay. Be back in 9 minutes.